So this lesson is on the gradient and the heat-seeking process. So remember, if a particle goes in the direction of the gradient, that will be the most efficient strategy in terms of gaining something in that third dimension. That will maximize the directional derivative, maximize the change in whatever that is with respect to distance traveled. So the most efficient route for a heat-seeking particle will be in the direction of the gradient because that will head it towards the warmest spot in that function. So a heat-seeking particle is located at the point 2, -1. It is on a metal plate with this temperature function. And we want to find the equation of motion for that heat-seeking particle. So it's always going to go where the heat is growing fastest, maximizing the directional derivative. Now, how are we going to do that? What's our strategy going to be? Well, let's go ahead and call that solution will be of the form R of t. So we're starting at 2, -1. We know that. And we'll say R of t is this vector value function, which is x of t, y t. Now R prime of t, which is the velocity of t, would then be x prime of t, y prime of t. Or using the other notation, dx dt, comma dy dt. And our goal here is to find that equation of motion. Our goal is to find R of t. So how can we do that? What do we need to use here? What fact is going to be important? The heat-seeking path will follow that path of greatest temperature increase. So what would that be? Where does that particle want to go? Which direction is it headed? If we're looking for greatest temperature increase, what is that? Of course, the answer to that would be the gradient. So it's got to head in the direction of the gradient of t. Well, what do we know? We have our function t of xy is 100 minus 2x squared minus 3y squared. So our gradient is what? We have to figure out the partial derivative with respect to x, which is -4x, and the partial derivative with respect to y, which is -6y. So that's our gradient. So we're following in that direction. The gradient of t is going to be the vector -4x, -6y. So here's our relevant information. And we know that it must head in the direction of greatest increase. The particle must head in the direction of the gradient. So let's just keep in mind what that would represent. If this is a vector valued function at this point, the way it's headed, what does that represent, the way it's headed? The way it's headed would be the velocity or the unit tangent vector or something like that. So if the way it's headed is the velocity vector has got to be in the same direction as the gradient. So what would that mean if the velocity vector is in the same direction as the gradient? That does not mean the vectors are the same. That means that the vectors are parallel. So v of t is parallel to the gradient of t, to del t. And what does that mean? If one vector is parallel to another vector, they're headed in the same direction, but they may be different sizes. So the velocity is simply a multiple, some multiple k of the gradient of t. And what is my velocity vector? Remember, velocity is r prime of t. So my velocity vector is dx dt, dy dt. Is some multiple k times what? Times -4x, -6y. Is there anything else I need to remember about this problem? Well, don't forget, in the beginning, we said the heat-seeking particle is located at 2, -1. So let's just make sure we realize that somewhere starts at 2, -1. which would tell me something about my position function. All right, so where do we go next with this? We have to think about these two pieces. So dx dt is some multiple k times negative 4x, and dy dt is that same multiple k times negative 6y. So with a little bit of algebraic stuff, I can get dx over negative 4x, dividing both sides by negative 4x is k dt. Similarly over here, dy over negative 6y is k dt. So if both of these things equal k dt, they would have to equal each other. So let's collect what we have and go from there. So collecting our information, we've seen dx over negative 4x equals k dt, and dy over negative 6y equals k dt. Therefore, they would have to equal each other. Dx over negative 4x equals dy over negative 6y. So we have this fact. Now, this is a separable differential equation, so we can't integrate both sides, but maybe to make our life just a little bit simpler, let's multiply both sides by negative 12. So negative 12 times dx over negative 4x equals negative 12 times dy over negative 6y. So what does that give me? That gives me 3 over x dx equals 2 over y dy. And then we have separated the variables. We've cleaned this up nice. So then our next move is to go ahead and integrate both sides. Integrate that side, integrate that side. What does that become? 3 natural log x equals 2 natural log y plus c. So we get there. Where do we go next? Well, using our rules of logs, natural log of x cubed equals natural log of y squared plus c. And then natural log x cubed minus natural log y squared equals c. Make sure we're clear on order of operations there. And then what? So we're still using our rules of logarithms to find the path of the heat-seeking particle. And using our rule of logs, the difference of the logs is the log of the quotient. So this could be natural log x cubed over y squared equals c. So then where do we go next with this? What's my next algebraic trick? The base of the natural log is e, so e to the c equals x cubed over y squared. E to the c is always positive, so I can ignore the absolute values. E to the c is x cubed over y squared. E to the c is a constant, so if we just think of it as being positive, I could say c is x cubed over y squared. In essence, it's absolute value. But I'm going to choose to ignore that. Multiply both sides by y squared, and I get c y squared equals x cubed. So now the next question is, how do I solve for c? What's the strategy I'm going to need to use to solve for c? What fact haven't I used yet? Well, it's this one right here. This solution goes through the point 2, negative 1. So x equals 2 when y equals negative 1. So making that substitution, what do we have here? Cy squared equals x cubed. C times y squared, negative 1 squared equals x cubed equals 2 cubed. C times 1 is c equals 8, which gives me what for my equation of my heat-seeking particle? 8 y squared equals x cubed. Now let's take a look at the geometry and see if that is reasonable. So here's the function for t. T of xy is 100 minus 2x squared minus 3y squared. So it is this paraboloid looking thing that goes up to 100. And then what is its vision in 2 dimensions? It looks like this. That's how far it goes out. So it's elliptical here, and then it goes all the way up to 100. Can you visualize the level curves? So I could have a level curve as small as z equals 0 up to z equals 100. So let's take a look at some level curves and see what we get. So our t was 100 minus 2x squared minus 3y squared. Could it equal 0? Where is that level curve? That's way out here. Can we visualize that as the base of that paraboloid we looked at before, right? That's the bottom in the xy plane. When we look at it like this, that is what we're looking at. How about 100 minus 2x squared minus 3y squared is 80? That looks good. How about equals 89? And the reason I chose 89 is because the point 2, negative 1, my starting point, is on that level curve. If I plug 2 in for x and negative 1 in for y, I get 89. How about 95? That's that level curve. So we're climbing the mountain. We're getting to the top of this curve. But remember, this is a temperature map. The hottest point is where? Is when we're 100, and that level curve is simply the point. That's all we have there, the point 0, 0 when we get there. Now, I said that the path of the heat-seeking particle was 8y squared equals x cubed. Does that go through that point? Let's take a look. It sure does, but I want you to notice something else, right? That heat-seeking missile is orthogonal to all of the level curves. We set it up so that we would be going in the path of greatest temperature increase. That's in the path of the gradient. And what do we know? The gradient is the path of maximum increase. That is the most efficient strategy to get to the heat source, which is at 0, 0.